So, it's 3 p.m. and you are in desperate need of a pick-me-up. You reach for that safety chocolate that you hid from yourself only last night and devour the entire block. Oh my, what is my body going to do with all of that sugar? Wow. That's where insulin comes into play. The pancreas, which is part of the endocrine and digestive system, consists of two major tissues, the acini and the islets of Langerhans. The islets of Langerhans, which are arranged around tiny capillaries, secrete insulin and glucagon directly into the bloodstream. The alpha cells secrete the glucagon and the beta cells secrete the insulin. Insulin and glucagon work in an antagonistic manner in the maintenance of metabolic homeostasis. So, the chocolate has been digested and glucose has entered the bloodstream. What next? Well, as glucose enters the pancreatic beta cells through the GLU2 transporters, it stimulates the beta cells to open calcium channels and increase calcium uptake. Calcium triggers a contractile mechanism where the microtubules stimulate the exocytosis of insulin-containing granules into the bloodstream. Insulin's action begins with the binding of insulin to a receptor. The insulin receptor consists of 4 subunits, 2 alpha units located in the extracellular space, and 2 beta subunits which span the membrane into the cytoplasm. Insulin binds to the receptor and causes the beta subunits to become autophosphorylated, leading to the activation of tyrosine kinase, which in turn leads to autophosphorylation of intracellular mechanisms. Intracellular vesicles containing glucose transporters bind to the cell's membrane and facilitate the transport of glucose into the cells by facilitated diffusion. Insulin also increases the permeability of the cell's membrane, allowing amino acids, phosphate, and potassium ions into the cell. The function of insulin is to store ingested nutrients. Directly or indirectly, insulin affects almost every cell in the body. Here, we will look at the tissues specialized for energy metabolism, the liver, muscle, and adipose tissue. In the liver, insulin promotes uptake, storage, and use of glucose. Firstly, insulin enhances uptake of glucose from the bloodstream by increasing the activity of glucokinase. So glucokinase is the enzyme that phosphorylates glucose upon entering the cell, which basically traps it temporarily as the phosphorylated glucose is unable to diffuse back through the cell's membrane. Insulin also increases the activity of many glycogen synthesizing enzymes, including glycogen synthase, which promotes the reaction of monomers linking to form a glycogen molecule. Insulin also decreases the rate of gluconeogenesis, which decreases the loss of plasma amino acids. Insulin inactivates liver phosphorylase, which prevents the liver from converting glycogen back to glucose. The overall effect is that glycogen is increased in the liver and excess glucose is removed from the bloodstream. Although if there is an influx of glucose into the liver cells, too much to be used for the local hepatocyte metabolism or glycogen storage, insulin promotes the excess glucose to be converted into fatty acids. So the fatty acids are packaged up as triglycerides in very low density lipoprotein and taken to the adipose tissue by the bloodstream. So within the adipose tissue, triglycerides are the most efficient means of storing energy. So how does insulin promote triglyceride storage? Well, insulin activates lipoprotein lipase within the capillary walls of the adipose tissue to cleave triglycerides into fatty acids for absorption. So once absorbed, the fatty acids are converted back to triglycerides and are stored in adipocytes. Some of the glucose taken up by adipose tissue is used to synthesize fatty acids, as well as forms a significant amount of aglycerol phosphate. So aglycerol phosphate supplies the glycerol portion used in the conversion of fatty acids to their stored triglyceride form. Also, by inhibiting the action of hormone-sensitive lipase, insulin prevents hydrolysis of stored triglycerides and thus inhibits the release of fatty acids back into the bloodstream. Moving on to the muscle, when engaging in moderate to heavy exercise, there is an increased permeability to glucose in the extended muscle fibers due to the contraction process. Through glycolysis, ATP is produced and glycogen is stored. Insulin then enhances the activity of glycogen synthesis and inhibits the activity of glycogen phosphorylase. Insulin also has the effect of promoting protein synthesis by increasing amino acid transport into the muscle cells and ribosomal protein synthesis, as well as inhibiting the catabolism of proteins by cellular lysozymes. In conclusion, insulin has many effects. Most importantly, allowing the glucose entry into the cells to be metabolized. Without insulin, the plasma glucose concentrations would be elevated, although the cells would be deprived of glucose.